Fluorinated gases such as sulfur hexafluoride, SF6, are extensively utilized in the semiconductor industry due to their exceptional dielectric and arc-extinguishing properties. However, these gases contribute significantly to global warming, and SF6 has been identified as the most potent greenhouse gas under the Kyoto Protocol. It has a global warming potential 24,000 times higher than that of CO2 and an estimated atmospheric residence time of 3,200 years. Despite environmental concerns, the dielectric performance of SF6 and ability to interrupt current have resulted in widespread usage as an electrical insulator and arc suppressant. To address the environmental concerns and economic challenges, the use of mixtures of sulfur hexafluoride and nitrogen as a replacement for pure SF6 has been proposed. However, the removal of SF6 from such mixtures to minimize the environmental impact and enable SF6 gas recovery poses significant challenges. Cryogenic distillation for separation of SF6 nitrogen mixtures is energy intensive, and in a recent publication in Chemical Engineering Journal, a cost-effective and stable aluminum MOF, in particular CAU-10-Py, that uses linkers such as shown here. This MOF is effective for separations of SF6 from SF6 nitrogen mixtures. The experimental data for transient breakthroughs of 1090 mixtures of sulfur hexafluoride and nitrogen in a tube packed with CAU-10-Py are shown here for two different inlet flow rates of the gas mixtures. The red symbols represent the breakthroughs obtained when the inlet gas flow rate is 2 milliliters per minute, and the black symbols represent the breakthroughs obtained at an inlet flow rate of 5 milliliters per minute. Now, these experimental data are from the Chemical Engineering Journal paper I referred to in my previous slide. Using the unary isotherm data and the ideal adsorbed solution theory, I simulated the experimental breakthroughs using a model that neglects intracrystalline diffusion limitations. For further details on the transient breakthrough simulations, I refer you to my video presentation on my YouTube channel. The breakthroughs for two different flow rates of 2 milliliters per minute at the inlet and 5 milliliters per minute at the inlet are shown here in red and black respectively, and these are comparable to the experimental breakthroughs that were determined experimentally. We note that the experimental breakthroughs have a slightly distended characteristics, indicating that intracrystalline diffusion limitations are not entirely negligible and need to be taken into account in proper description of the separation performance of SF6 nitrogen mixtures using CAU-10-Py. That's the message that emerges from my presentation here, that for modeling breakthroughs precisely to match experimental measurements, we need to take account of intracrystalline diffusion limitations.